Hi guys, BuildZoid here, and today we're going to be taking a look at how load lines work on the Intel LGA1700 socket, and basically why Intel had to add a voltage limiter with the 129 microcode that stops the CPU from requesting more than 1.55 volts from the motherboard. So let's get into it. Now, this is going to be really long because we need to basically go through how voltage regulators work. In terms of the some of the functionality of the voltage regulator. So anyway, this is a Z790 Aorus Pro X motherboard. The vCore VRM on this board, well, technically it should be just vCore VR instead of the M stands for module. So and it's not it's not a module that like slots into the board. But anyway, so the vCore regulator, so VR, is this set of phases over here. And the controller for those is this chip over here, right? And the way the controller controls the output voltage of all of the phases is that it sends a PWM signal to the power stage, and that just switches the power stage on and off. And depending on the pulse width of the PWM signal, you get more or less voltage, right? So that's like the basics of how our controller works. Now, obviously, the controller needs to measure the voltage that is coming out of the phases, and it needs to measure it somewhere, right? And depending on where it measures it, things can get like you're gonna like it's either gonna work or it's really not gonna work. So because of that, Intel actually provides a dedicated measurement connection for the CPU. So this is the first thing I want to make absolutely crystal clear, because I see a lot of people just not understand this. The voltage regulator measures the voltage at the CPU. It doesn't measure it on the motherboard. It measures it at the CPU through pins provided by Intel to get a accurate voltage measurement of the voltage at the CPU, okay? It measures at the CPU. It regulates the voltage at the CPU. It does not care about the voltage on the motherboard because it doesn't measure that. It has literally no idea what the voltage at each individual phase is because that's pointless, okay? It doesn't need to know that. It just needs to know what the voltage at the CPU is. So Intel provides these two pins right here to do that, and they provide two pins because when you have lots of current flowing, you need to measure both the hell. Okay, let's start over. They provide two pins because voltage measurements are always relative between 2 points, right? So a single point in space does not have a voltage. If you have 2 points, then you can measure the voltage between the two points. So Intel has to provide both a negative pin and a positive pin so that you can measure between them. And you can basically think of these as one end is vCore and the other one is ground. And this is really important that they provide both a negative and a positive, because if they only provided one pin, the amount of current that is flowing, right, because current always flows in a circle, right? Like it always has to return. So if you have 200 amps going into the CPU, you also have 200 amps going back out of the CPU and into the voltage regulator, right? So you have this like 200 amps of current flowing, which means that there is a voltage drop between the low side MOSFET which is the MOSFET that like handles the return current, and the CPU silicon. Like there's if you measured, now unfortunately, I guess we could so if you found out which side of one of these capacitors is negative, right? So let's just say it's this side. I don't know. I didn't bother to check. It doesn't really matter. But like if you measured from the negative over here versus say the actually this is probably the ground pad, or yeah, this is probably ground. So if you measured from like here to the ground of the CPU, you would actually see a pretty substantial voltage drop because of all of that current that is flowing back from the CPU and towards the voltage regulator. Which means if Intel only provided one pin for the voltage measurements, the voltage controller, if it was measuring the voltage at the CPU relative to its own ground, it would measure a higher voltage than what the CPU is actually getting. So that's why Intel provides 2 pins, not 1, because if they provide, well, or actually why they provide any pins at all, because if you didn't have any pins, then you would actually just have no idea what voltage the CPU is getting whatsoever. It would be just completely all over the place. Yeah, so the voltage regulator has a measurement connection directly to the CPU, and we'll call this the feedback slash you'll see it sometimes called vCore sense. Annoyingly enough, some motherboards get really weird about labeling things vCore sense, especially MSI has like a VCC sense thing that doesn't measure correctly, but if motherboards were motherboards, man. In this case, the issues that Intel is dealing with the excessive voltages that the CPUs are getting, that's not the motherboard's fault. But the fact that if you fire up a hardware info on a bunch of LGA1700 motherboards, getting accurate voltage measurements is really hard because the motherboards don't give you access to the measurements from the voltage controller. They just don't. And this is for a good reason, because this feedback circuit is very sensitive. So you don't really, the chip that most of your monitoring software actually pulls up is the Super I/O chip. And the Super I/O chip lives, somewhere down there on the motherboard. So you don't really want to go grab your very, very sensitive feedback circuitry, sense wires, and run them over to the Super I/O that's on, the bottom edge of the board somewhere. That would be pretty bad, because if you run that wire past I don't know, if you run it past a voltage regulator or something, you're gonna have a bunch of junk in your feedback circuitry, and then your VRM isn't gonna work correctly. So it's for a good reason that this circuit, this connection is exclusively used for the controller. And there are some high-end motherboards like this one that actually do provide access to the feedback, the vCore sense measurements. But they require extra circuitry because there's no there's no requirement for the motherboard to provide you with accurate software voltage readings. That's just not a thing. Nobody cares. So here we are. But yeah, some high-end motherboards will basically give you a op-amp, so that's what this chip is. And all this chip does is it copies the voltage from the feedback circuitry that's going to the VRM controller, and then it outputs that over to the Super I/O. And this is fine, because even if there's a bunch of garbage on the Super I/O side of the connection, it doesn't get fed back into the feedback circuitry, right? So the feedback circuitry is not... is still safe from whatever is going on with the wires connecting to the Super I/O. And Gigabyte does this on some of their boards. Asus does this on a bunch of their boards. MSI doesn't do this ever. They have you know what, I'm not going to bother being nice. They have a half-assed implementation where I think they only take the positive end of the feedback circuit and send that to the Super I/O. So it reads 30 millivolts high at 100% load, but oh well, And ASRock, I don't think does this at all either. So yeah. Though if you're lucky, on some motherboards you can just directly pull the voltage controller, but that doesn't always work either. So yeah, because some motherboards just straight up block access to the controller itself, and then a lot of the time the controller just isn't supported by the monitoring software, so you can't get a reading from the controller anyway. But where was I? Right, so we have this feedback circuit, and that's what the controller uses for monitoring the voltage at the CPU. And unfortunately, you probably don't have access to the very accurate, high-precision voltage measurements that the controller has, because that's just not a part of the design concerns of the LGA1700 platform. Now, you might also be wondering, well, what if these two pins break? Wouldn't that be really bad? Yes, it would be really bad, and so there is a fallback connection. Typically, that's implemented in the form of a pair of resistors that'll just connect somewhere on the motherboard, usually inside the CPU socket. So if you look over here, so that connection will be made into somewhere in this area, right? And the point of this fallback connection is, the way this is set up is usually you'll have 100 ohm resistors. And the whole idea is that if these two pins get disconnected, then you still get a voltage measurement from the motherboard, right? But it's not accurate, but at least you don't end up in a situation because if this didn't exist and your pins broke, what would happen is the VRM would fire up, and the voltage at the pins would they'd just be floating, right? So they might be at 0 volts, they might be at something really high. And if they're at 0 volts, then the voltage controller is well, the voltage is 0, so obviously I need to increase the PWM signal. So the voltage on the output would progress, just shoot upwards, right? Because the controller is I'm raising the PWM signal and the output voltage is still 0, and it's still 0, and it's still 0. And luckily, most modern high-end controllers do have a max PWM width, so they'll just if they hit 30% or something, they'll just cut out because something's evidently wrong. Actually, I don't think it's 30%, but there is a max PWM pulse width at which they will just shut down. So even if the connection is gone, your output voltage won't just shoot past 3 volts or something, but 2 volts is already plenty to more than enough to destroy a CPU. So you do need this backup circuitry of these 100 ohm resistors, so that if the pins to the CPU break, the voltage controller at least can still see what the output voltage of the regulator is, right? And the reason these are 100 ohm resistors is the connection to the CPU is lower resistance than these resistors. So if the CPU, if there's nothing wrong with the socket, then the voltage from the CPU overrides the voltage that's sort of coming into the circuit from the through the resistors, right? So that's what's going on with that. And for the purposes of this video, you can basically forget that backup circuitry, backup feedback circuitry exists. But I've felt it's necessary to point that out because, yeah, it does exist. Your motherboard, your voltage controller, if something goes wrong with the connection to the CPU, doesn't just blow up your CPU, okay? At least if the motherboard is designed properly. I've never seen a motherboard that doesn't have the fallback connection, but I don't know. Technically, it's not it's probably required, but yeah, I guess if you shaved the if you had a banged up secondhand motherboard, right? Maybe they somebody shaved off the resistors and then they bent the pins, and then yeah, then you'd be screwed. But generally speaking, not a concern. So anyway, the controller monitors the voltage at the CPU, at the silicon, okay? The CPU tells the controller what voltage it wants over the SVID interface. So we're just going to draw that out over here. All right, so this is just a digital output. The S in SVID stands for serial. So it basically just sends a string of ones and zeros. Other VID standards are things like you have PVID, which is parallel VID, where you'd basically, instead of having one, well, SVID has one data line and then there's a clock line, right? But for PVID, you'd basically had 7 or 8 pins on the controller, and you would encode the voltage by pulling pins high or low. Then there's PWM VID, which is what NVIDIA uses, where they just use a PWM signal to the controller, and then the controller converts that PWM signal into a voltage level. So, there's a bunch of different ways, but Intel uses SVID, where they just send a string of ones and zeros and a clock signal on a second wire so that the controller can decode that into voltage requests. So if our CPU sends a SVID request for 1.2 volts and we have, and we don't have a load line, right? Then the controller is just gonna look at the voltage at the end of the sense circuitry, right? It's gonna look at the voltage. I don't actually know where those pins connect on the CPU, but probably pretty close to the silicon. Because it's worth pointing out, if you look at the pin out here, like these red pins, these are all V-core. And now I haven't checked this for LGA1700, but my past experiences with other Intel CPUs is that just from like here to here, you already have a significant voltage drop on the CPU substrate itself, right? So if you so that connection has to go to the silicon. Like it can't just connect to some random, like it needs to go pretty close to the CPU. It can't just go to some random place on the substrate because you'll notice also this one's upside down, right? A corner. Those are our corners. So, wait, if that's... Now I'm confused. We'll just pretend that V-core comes in over here. So if you measured the voltage over here, that's going to be different than the voltage over here. That's going to be different than the voltage over here. That's going to be different than the voltage on these capacitors. So, I don't know specifically where exactly the voltage regulator sees the voltage on the CPU, but it is wherever Intel intends for it to be measured. So, we'll say it's somewhere near the center. Anyway, so the controller goes like, okay, I need to get 1.2 volts over here, and it just sends a PWM signal to the power stages that leads to the voltage over here being 1.2 volts. Now, why do I say leads to the voltage at the CPU being 1.2 volts? Well, if we don't have any current flowing, right, if we have 0 amps, then this is pretty simple. You just 1.2 volts at the inductors means 1.2 volts at the CPU. So in that case, we can just send a PWM signal of 10% and all is well, right? Because we have 12 volts coming into the power stages, and we're just going to pretend that it's 12, just straight 12 volts, right? So we have 12 volts coming in, 10% PWM signal, 1.2 volts comes out, we get 1.2 volts at the CPU, all is well. But this is with no current flowing, so this isn't realistic because CPUs, current flows through CPUs, at least if they're actually doing something. So let's say we're outputting 10 amps. Well, if we're outputting like 10 amps and the motherboard, then obviously the issue we run into is that the motherboard and the CPU socket and the CPU substrate, they all have resistance, right? And from my personal experience, the socket itself seems to have about, based on measurements that I've taken, the socket for LGA1700 seems to be about 0.2 milliohms, all on its own. So that's before you even account for the motherboard. And then for the power plane of the motherboard itself, right, because you basically need to somehow... this is an 8-layer board, so technically there could be a connection on an internal layer that goes over here, right? This is a bunch of E-core pins over here. So, technically there could be a connection there. But if you have a cheaper board that's, say, a 6-layer PCB, the power from the phases down here probably just has to do this. And same for, so all of the current ends up having to squeeze through the top corner of the CPU socket, which leads to some funny thermal situations if you have a really crappy board where this area of the board gets really, really hot because all of the current has to squeeze through there to get into the CPU socket, which is great. And anyway, so yeah, the motherboard has some resistance, the socket has some resistance, the CPU substrate has resistance, which is why we have that connection all the way to the CPU. So, let's just say all of that adds up to a resistance of 1 milliohm. Well, if we're putting 10 amps through a resistance of 1 milliohm, the voltage over on these inductors, like, we're going to have like 10 millivolts of voltage drop, right? So the voltage on our inductors has to be like 1.21 volts. But like I drew earlier, this inductor down here, right, this phase down here is significantly further away from this corner of the socket than, say, this phase. So in reality, the voltage over here might be like 1.211. Here it might be like 1.209, and you get the idea. So every phase, like on a running motherboard, every single phase will actually have a slightly different output voltage. Which is why the controller doesn't measure the voltage on the motherboard, because that would just make, like, it would be a horrible mess. Every motherboard would like do different things. And then depending on how good your socket contact, right? Like imagine if like you have less or more mounting pressure and that affects the contact with the pins for the CPU, it's like, yeah, no, this isn't going to work. So that's why the controller measures the voltage at the CPU. And then it just, and the funny thing is, like, it's not even, the controller, technically it can try to balance the current through each of the phases, because it does measure the current flowing through each phase, but it doesn't know the output voltage for each phase. So the controller can do things like send a slightly shorter PWM pulse width to the phases that are outputting more current in order to push some of that current over to the other phases that are working less hard. And this is like a efficiency optimization primarily, is making sure that the current really is evenly spread across all of the phases. Though some controllers will also do something, like I think Asus does this on some of their motherboards, where they'll actually spread the current based on operating temperature, not balancing, which could actually lead to better efficiency than the the even current spread setup. But anyway, so the point is, like, the voltage at each of the inductors is going to be slightly different, and the controller neither knows nor cares, because it measures the voltage at the CPU, and as long as, like, CPU asks for 1.2 volts, CPU gets 1.2 volts, what the output voltage from the inductors is doesn't matter, right? Literally, controller doesn't care. Now, if we're outputting 100 amps, things get, well, more complicated, because at 100 amps, 1 milliohm of resistance means that we're just going to pretend that our VRM has now turned into a point source of power instead of what it actually is, which is a bunch of different phases. And so, on average, the VRM will basically end up at like 1.3 volts now, right? Because we have that 1 milliohm of resistance. Now, again, in reality, you would end up with like the really far away phases sitting significantly higher voltage and the nearby phases sitting at lower voltage. But point is, yeah, so, 1.3 volts over here, but the CPU is still at 1.2 volts, right? Because the controller measures the voltage of the CPU. It doesn't care that there's 1 milliohm of resistance. It has no idea. There could be 2 milliohms, and then it would just set this to 1.4, and it still wouldn't care, right? Because it measures the voltage at the CPU. And obviously, if we keep going up in output current, like if we hit 300 amps, right, then the voltage at the VRM is going to be like 1.5 volts, because 300 amps through 1 milliohm. The PWM signal width is going to be about 12.5%. And the voltage at the CPU is still 1.2 volts. It's great, right? Like, the controller just deals with this. So why do we need load lines? Well, the thing is, all of this that I've described here is for steady state. So that means the current isn't changing, right? If the CPU is continuously pulling 300 amps, then yeah, the voltage at the inductors is going to be something around 1.5 volts, and the voltage at the CPU is 1.2 volts. But what happens if the CPU suddenly goes from 300 amps to 0? All of that voltage drop that we have through the power plane because of our high current draw just disappears, right? And to make things worse, we have a bunch of excess energy stored in the inductors. Because the current flowing, like, inductors store energy based on how much current is flowing through them. So if you want to quickly go from having a lot of current flowing through an inductor to having less current flowing through the inductor, that energy in the inductor needs to go somewhere. So on a so when the CPU transitions from like 300 amps of, like steady state to 0, yeah, the voltage suddenly, like, it goes from 1.2 volts to basically like 1.5 or higher. It just shoots through the roof, right? Because you have, like, first of all, the board is like charged to like 1.5 volts anyway, right? These capacitors are literally right on top of the inductors. And then, of course, you have all the extra energy stored in the inductors themselves, and you basically end up with a nice big fat voltage spike that goes over 1.5 volts. Not ideal. So, but ultimately, like, this isn't really, like, as long as the spike isn't too big, it's not actually going to damage the CPU, so this isn't too concerning. But the bigger problem is the opposite transition, where you go from 0 amps to 300, right? Because if the output voltage, or let's say from 10 amps to 300, right? Because in that scenario, the voltage, like at 0 amps, right, the VRM is like at 1.2 volts. And here is at 1.2 volts. But this resistance exists. So if we suddenly ramp up to 300 amps, the voltage at the CPU is just going to fall off a cliff. Right? And the controller also doesn't react instantly, and the power plane does have some inductance to it, and the inductors have a lot of inductance to them. So you end up in a situation where, if you're at 0 amps, and then suddenly the CPU jumps to 300 amps, the voltage temporarily falls off a cliff, right? And at some point, the controller is like, wait a minute, this isn't 1.2 volts, this is 1.18. I need to do something about it. So it starts turning on the phases. So most modern controllers can actually turn on multiple flip phases at the same time. If it's a smaller load step, it might just increase the PWM signal width, right? Or if the transition is slower, like if you go from 0 amps to 300 amps very slowly, the controller might just progressively increase the PWM signal width, and no big deal, right? But if you have a really fast transient, where the current draw jumps in the span of like a fraction of actually, like, not even a fraction of a millisecond. We're talking in like the range of microseconds, right? That the current ramps up from like 0 to 300 amps. Yeah, the voltage just kind of nosedives. And then the controller eventually like catches it and manages to pull the voltage back up to where it's supposed to be. But if you're a CPU manufacturer, and, you have a target operating voltage of 1.2 volts, right? So it's like, oh, I want 1.2 volts in order to run 5 gigahertz. And your CPU is happily running, like here it can run 5 gigahertz. And here you can run 5 gigahertz. That's not a G. So here you can run 5 gigahertz. But the bottom of this might be like, I don't know, 1.1 volts. Well, this will not run 5 gigahertz. This will run maybe 4.8 or 4.9 or something, right? Obviously, like, depends on the silicon. So if you have a chip running at 5 gigahertz and your voltage suddenly does this, your chip crashes is what happens. Unless you have some kind of fancy clock stretching mechanism like what AMD has or what NVIDIA has, or even Intel at this point. Like, as far as I can tell, they do have clock stretching now. But anyway, if you don't have clock stretching, like, say, when load lines were first implemented, yeah, this will actually just, like, crash your CPU. So this is not good. And so CPU manufacturers and, like, voltage regulator manufacturers came up with the idea of load lines. Which don't really solve the problem of, like, oh, the voltage jumps off a cliff, but what it does solve is, like, the thing is, okay, well, let's bring this all back. Like, it doesn't really solve the fact that, like, the voltage just inherently wants to fall down to 1.1 volts. But pulling the voltage back up to 1.2 volts if you're limited to 4.8 gigahertz due to the voltage regulation, right? Like, you can't, like, if this happens and you want your chip to be stable, you have to be like, okay, it's actually 4.8 gigahertz at 1.2 volts, right, then this is like a massive waste of energy because you have all of this voltage over here that you can't actually use because if you clock the chip to 5 gigahertz and there's a sudden transient, it crashes. But if you clock the chip to 4.8 gigahertz, well, you don't need 1.2 volts. But you also can't just drop the, like, you can't, lower the chip to 1.1 volts, 4.8, and then 1.1 volts, 4.8, because if you start at 1.1 volts, right, your voltage dives again and ends up at 1 volt now. So load lines were initially implemented as a efficiency optimization, basically. Because, yeah, if you're, like, your voltage regulator just, it can't maintain perfectly flat voltage. It's physically impossible. Even, like, you have the delay of the, like, first of all, the controller needs to notice that the voltage is dropping, right? And that doesn't happen instantly. The controller isn't instant. It needs, like, it takes time to measure it. It takes time to adjust the PWM signal widths. It takes time for the MOSFETs in the power stages to turn on. It takes time for the current through the inductor to ramp up. And then your power plane itself has some amount of inductance, as well as the pins and the substrate. So, even if you removed the, measurement delay, the voltage would still fall off a cliff. Maybe not as much, but it would still fall off a cliff. At some point, CPU designers and voltage regulator designers decided, well, okay, if we can't, if we have these massive just undershoot spikes that cause instability, there's no point pulling the voltage back up because we can't clock the chip any higher, even if the voltage recovers eventually. So instead, they added load lines, which basically just let the VRM sag the voltage based on output current. So in this scenario of we have this setup here where it's like, okay, 1.2 volts at, and the target the CPU sends an SVID request for 1.2 volts. If we tell the controller, right, that load line equals, this is not going to fit. So we say the load line equals 1 milliohm. Right? Now, when we go from 1.2 volts, the voltage dives, right? So now this is like 1.2 volts at 4.8 gigahertz. So, yeah, we are clocking the chip lower, but, you had to do that anyway previously, right? Because your other option was yeah, the voltage still hits this minimum point, and then you pull the voltage back up and you have higher power consumption by 10%. Actually, it's not even 10%. If you have undershoot, if you have an average operating voltage of 1.2 volts with an undershoot of 1.1, you basically have 20% extra power consumption for no extra stability in terms of operating frequency, because your average voltage dictates your power consumption, and your undershoot dictates stability, right? So if you have 100 millivolts of undershoot, you're literally just throwing efficiency out the window. So anyway, unless you have a clock stretching mechanism. So anyway, so here you'd have 1.2 volts at 0 amps, and then here you'd have 1.1 volts at 100 amps, right? Because we set our load line to 1 milliohm. So the voltage controller gets a request for 1.2 volt. It gets a request for 1.2 volts, and basically what it does is 1.2 volts minus 1.2 volts minus 1 milliohm times 0 amps, right? And that just is 0. So 1.2 volts minus 0 equals 1.2 volts. Over here, it does 1.2 volts minus 1 times 100. Again, it's 1 milliohm times 100 amps, right? And that spits out 1.1 volts, right? And then on the load release, the voltage just cleanly recovers back up to 1.2 volts. So this is basically how load lines work on Sandy Bridge CPUs, LGA1366, Bulldozer CPUs, Ivy Bridge, Skylake. Yeah, most of the early Skylake stuff, KB Lake. Yeah, so this, like, you know, like, if you look at this, it kind of looks weird because it's like, but like, your voltage is lower. Like, why would you want this? And it's like, well, because, again, like, yeah, you could pull the voltage back up, but, like, you still can't run more than 4.8 gigahertz, so why even bother, right? Like, why bother pulling the voltage back up? Also, with this load line setup, you can actually get away with less capacitors, which is cheaper, and we all know that manufacturers love things that are cheaper. And the reason you can get away with less capacitors is because, especially like the big bulk capacitors, these are entirely too far away and too slow to really do anything about this right here. Like, through-hole aluminum polymers, great for absorbing, like, big voltage spikes coming from the inductors. Kind of useless for preventing a brownout on the CPU, right? Because they're not on the CPU. They're like a mile away, behind all of the resistance of the power plane, all of the resistance of the pins of the socket, all of the substrate resistance, right? So, like, these capacitors over here are basically the only thing that really affects how quickly this falls off a cliff. So, yeah. Life is very hard for CPU power delivery. But if you have a load line, right, like, you don't need as many, like, you don't need so many bulk capacitors to absorb the, like, excess energy from the inductors on the load release because you're now starting at a lower voltage, right? So you can, like, throw a bunch of your bulk capacitors out and it just makes your boards cheaper. So that's cool. So basically, load lines, like, the whole point of load lines is, like, you get better efficiency at 100% load, not at idle, right? Like, obviously, your idle voltage is still 1.2 volts, so your idle power consumption hasn't changed, but at least when your CPU is pulling 100 amps, well, it's pulling 100 amps instead of, because here's the thing, if this was 1.2 volts and your frequency didn't change, I can tell you from just, like, from experiments I've run in the past, your current draw is going to be basically 110. It's actually going to be a bit more than that. Right? So I guess if we drew it as like a separate line, I'll do that in red, and we had that spike, right? Like, your options are basically 4.8 gigahertz, but with 1.2 volts and like 110 amps versus 4.8 gigahertz with 1.1 volts and 100 amps, right? And notice how, like, power consumption is voltage times current. Here, both your voltage and your current is higher. So this is significantly less power efficient than this, right? So that's why load lines were implemented, was because, like, well, the voltage regulator, like, it is physically impossible to design a power delivery system that isn't going to have undershoot. Okay, it cannot be done. Like, laws of physics prevent it from happening. So, since you're never going to get the voltage you want anyway, you may as well just kind of go with the flow, if you will, right? Oh, the voltage wants to jump off a cliff? That's fine. We're not going to fight it. The voltage wants to jump up? Cool, right? And the end result is you get a cheap, like, you don't need to have so many bulk capacitors, your power efficiency is better. What's not to like, other than the fact that you can't run 5 gigahertz anymore, right? So, but it's like, well, previously you couldn't run 5 gigahertz anyway. Like, previously the 5 gigahertz didn't really work either, so, you know, not actually a loss. So that's what load lines do. Right, is that they just droop the voltage based on output current. And for low current CPUs, this is fine. This doesn't really cause any major issues because, yeah, if you have a CPU that, you know, has a peak current draw of like 100 amps. You just idle it at like 1.3 volts and then you get your 1.2 volts under load and everything is cool. Or you idle it at 1.2 and you get 1.1 under load and everything's cool. But when you design CPUs that have, and this is like Sandy Bridge, LGA1366, like those CPUs had a like operating voltage of around a volt, maybe 1.2. They pulled like a maximum of 100 amps. So yeah, it was cool. You had your 1 milliohm, 1 milliohm load line slope. The voltage droops by 100 millivolts. Everything's fine. No big deal. But then you get to something like, say, a 14900K, right? And a 14900K brings some very real problems to this. I wonder if I could just grab the eraser for this. What is the eraser shortcut? Oh, it won't tell me. Oh yeah, it will not tell me what the eraser shortcut is. Technically, the back of my pen has an eraser, but I don't think I have it like configured to work. Oh, why are you like this, GIMP? I wish the pen, like the eraser and the paintbrush didn't share brush sizes. That's like so annoying. I bet there's some way I can change that. Anyway, so if you have a 14, so that was like an example of like, 1.2 volts, 100 amps, load line, just kind of like you get extra efficiency and everything's cool. No big deal. But then you get to something like a 14900K. This is a 13900K, but, 14900K. And the all-core clock, right, turbo, is like 5.6 gigahertz. And now my CPU is an absolute potato, so it's like 5.6 gigahertz at 1.38. But let's say you don't have a potato and it's 1.3 volts. So that's not that high, right? But then you run into the problem that a 14900K has an ICC max of 307 amps. So, you know how with 1 milliohm of load line slope at 100 amps, the voltage droops by 100 millivolts? Yeah, with this, it droops by like 307 millivolts. So if you want to get 1.3 volts at the CPU, you need to ask for 1.6 to the voltage regulator. All right? And that's bad. That's just like, yep, that's not really a good idea, is it? And that's unfortunately exactly what Intel does. And actually it gets worse because Intel's like max, right? The max ACLL for LGA1700, man, my L's are looking like C's, is 1.1 milliohms, right? But now Intel isn't completely stupid, so they don't actually idle your 14900K at, 1.3 volts plus 307 times 1.1 milliohms, because yeah, that would be really, really dumb. That would probably destroy your CPU in a few hours. Okay? That really wouldn't take very long to take your 14900K back to being sand. So how does Intel like avoid this issue? Because at the end of the day, right, if the voltage regulator is set to 1.1 milliohms, then in order to get 1.3 volts at the CPU, you need to send a VID request for 1.6. Like, there's nothing else you can do. So how does Intel avoid that? Or at least try to avoid that? Well, they look at how many cores are active. And this is why you might notice that in the statements that Intel has released about preventing degradation on their 13th gen and 14th gen CPUs, they keep like saying that you shouldn't use the high performance power plan for Windows because the high performance power plan, I guess, is like less fast to put the cores to sleep, or it might keep them awake longer. And basically, the CPU, like if you have one core boosting, it doesn't do 300 amps, right? If you have one core, I think it's like one P core equals, I think, about 50 amps. Because I don't know what it is for sure. Two P cores, it might be like 100 amps, right? And so this is like an extra 100 millivolts. 4P cores, and now things start getting, awkward because 4P cores can pull an incredible amount of current. So I actually don't know what this would be for the like expected peak current, but let's just say it might be 200 amps, right? And so on and so on. And eventually you get to the 24 core configuration, and the expected current equals 307 amps. Actually, it's more than that as far as I know, but we'll just go, like, it seems to be pretty close to 307 amps. And the reason I say it's more than that is I actually tested for this with the i5. I didn't test for this with the i9 because it's uncoolable. But with the i5, I tested for this, and the max VID request sort of stops changing above 200, like somewhere above 200 amps. And the ICC max for the i5 is 200. So like going from 200 amp ICC max to 225, there's still a increase in max voltage. Actually, you know what? I'll just pull that up. Where is it? Oh, yeah, here we go. So this is from a 13600K, VRM set to 1.1 milliohms, AC load line set to 1.1 milliohms, and you can see how peak voltage with 500 amp ICC max is the same as it is at 250 amp ICC max, but 1.468 for 225, 1.436 for 200, 1.41 for 175, and you'll notice that like this step right here is about 25 millivolts. Right? 1.436 from 1.411 is about 25 millivolts. Why is it about 25 millivolts? Because 1.1 milliohms times 25 amps is about 25 millivolts. It should actually be a little bit bigger than that, but, maybe I just didn't take enough peak measurements. And the same thing happens here. You go from 200 to 225, and we see about another, like, what is it? 22 wait, no, that's like 32 millivolts more peak voltage. So there might be some like extra overshoot getting mixed in from the VRM. But as you lower the ICC max, the max voltage gets progressively lower. And then you see basically the same thing for the different load lines. I tested also 0.55, and you'll notice that, like, yeah, if you set the lower AC load line, you get lower peak voltages. Because, like, Intel, like, and here's the thing, I'm, like, I don't see another way of dealing with this either. Because if you don't have clock stretching, then yeah, like if you want, like if the board has 1 milliohm of like impedance and the voltage regulator is set, and even if the voltage regulator isn't, like, it doesn't actually matter if the board has 1 milliohm or doesn't, right? Because let's say I have a let's say I have a 0.5 milliohm motherboard, right? And the voltage regulator set to 1.1 milliohms. Well, the voltage regulator measures the voltage over here, right? So the target voltage for the voltage regulator, if I say, I send a VID request for 1.6 volts, right? And I send that down my SVID interface, and there's 300 amps flowing from the motherboard, then, our 1.6 volts gets to the voltage regulator, and the voltage regulator does 1.6 volts minus 1.1 milliohms times, and then actually, you know what? For fun, let's do 200 amps. Just to illustrate like the flaw of this whole system that Intel came up with. So times 200 amps, you know, and then that works out to 220 millivolts. So that's going to be like 1.38 volts, right? So this is what the voltage regulator actually aims for. So 1.38 volts over here. And then the board impedance is 0.5. So the VRM is going to be at 0.5 times 200. That's 100. So this is going to sit at 1.48 volts. Right? The board impedance is irrelevant. If the impedance of the board was 1 milliohm, then 1 milliohm times 200 amps is 200 millivolts. So instead of 1.48, we would sit at 1.58. This still doesn't match the VID request, right? Because it doesn't matter. If the board was, like, if the board was 0 milliohms, right? Well, 0 times 200 amps is still 0, so 1.38 volts. This is, of course, physically impossible because the CPU socket itself has more than 0 milliohms of resistance, so... just having, like, and even if you were like, oh, well, instead of a socket, let's use solder balls. Well, guess what? Solder balls have resistance. They're not superconductors. And here's another sort of fun fact. The resistance of the motherboard changes based on operating temperature. Quite significantly, because copper's like resistance changes with temperature a lot. So if your motherboard is at room temperature, the resistance of the board is actually lower than, say, 2 hours of rendering workload later, right? If the board temperature goes up by, like, if you go from 20 degrees to 100 degrees Celsius, the output voltage at the inductors is going to be significantly different. The voltage at the CPU is not going to change because the voltage regulator measures the voltage at the CPU, and it applies the load line as a target. Right? It doesn't apply the load line as like it's not meant, like the load line slope from the voltage regulator isn't meant to compensate for the resistance of the board. That's not what it's like. It is kind of meant to do that, but not in steady state, right? If the CPU is pulling a constant 200 amps, the impedance of the board is utterly irrelevant. It doesn't matter. The only time the impedance of the board and the reason why we try to match the load line to the impedance of the board is that if you have if you have a impedance mismatch, right? So let's say you have a 0. Let's say you have a 1 milliohm board, right? And you have a 0.5 milliohm load line at the VRM. What you're going to get is this. So you have all this undershoot, right? And then on the load release, you're going to get a bunch of overshoot. So you get all of this and all of this because of your impedance mismatch. Because the voltage regulator is like, well, you know, like here you might be at 1.2 volts. Let's say this is 100 amps. So here you're going to be at 1.25. But the board, like the impedance of the board causes undershoot into the 1.1. I mean, not 1.25 is going to be 1.15. But the board is undershooting, like the impedance of the board causes undershoot into the 1.1 volt range. Right? So if you have an impedance, like if your load line is shallower than the board impedance, you get undershoot. It doesn't affect the average voltage that the CPU sees. And if you do the opposite, where like, let's say, you know, you swap the load lines around, or like we swap the impedance and the load line from 1 milliohm and 0.5, we go 0.5 equals board, and 1 milliohm, you know, equals VRM, LL, then all that's going to happen is you get this. Like, there's no extra undershoot because it's like basically the voltage on its own jumps up to about here, and then the voltage regulator pulls it up the rest of the way. So actually, you might get something that looks a bit like your waveform might look a bit funky. It might look like this, right? And actually on this end, you might get something like it'll give you like more of a bowl shape because the voltage regulator will have to pull the voltage. Like you'll get the initial 0.5 milliohms of undershoot, and then the voltage regulator like has to manually pull the voltage all the way down to hit that 1 milliohm load line. And then same thing on the opposite end where it like has to manually pull the voltage back up. But it doesn't cause any overshoot and it doesn't cause any undershoot. It's not a problem. Like the point I'm trying to make here is that if you have a really good board and you set a massive load line on it, nothing really happens. You just get a bunch of V droop. It doesn't do anything. So the problem that Intel basically has is, you know, is that they need to offset their VID request by the expected V droop so that the voltage at the CPU is high enough for the CPU to function. Right? Because, yeah, if, like, the CPU is trying, like, I want to run 5.6 gigahertz all-core at 1.3 volts, then I need to send a VID request for 1.6 volts. Because here's the thing. Let's say you're, and we can see this with the i5 testing that I did. Man, so apparently I have two instances of this. Okay, this is the right one. So you can actually see this when I do some Prime 95 testing with very high V droop, right? So with 0 V droop, you can see how Cinebench and Prime 95 basically run at the same voltage. Prime 95 is slightly higher voltage because the temperature that it runs at is higher, right? Prime 95 pulls more current. But at 1.1 milliohms of load line slope on both the VRM and the AC load line, you'll notice that Prime 95 actually runs at less voltage than Cinebench, which is nuts because Prime 95 needs, like, from a overclocker, like if you're static overclocking, right, Prime 95 needs more voltage for stability than Cinebench does. But the problem that's causing this, like, higher operating voltage in Cinebench is that the CPU, like the voltage regulator has 1.1 milliohms of V droop. And so, you know, for Cinebench, all of the cores are active. It's an all-core workload. So the CPU is sitting there and like going like, well, you know, what if Cinebench suddenly turns into Prime 95? Right? Because if Cinebench was running at the Prime 95 voltage, then if suddenly Cinebench turned into Prime 95, the voltage would be too low, right? You would go from 1.099 to like 1.06, and then you would crash, at least if the CPU was binned within 30 millivolts of not being stable anymore, which it isn't, but... So that's like the whole concern. And this is like the whole issue that Intel has with their like power delivery on LGA1700 is that they have a load line slow, like they're using a load line system that was good for like Sandy Bridge CPUs and LGA1366, right, where it pulled maybe 100 amps out of the box. But with a 14900K, like you have this very real problem of like, well, okay, I have a 24 core, like I'm running an application on 24 cores that pulls 200 amps, but like there's like the slightest possibility, and this isn't even that bad, right? But you have this like, okay, it's pulling 200 amps. What if it suddenly pulls 300, right? So you need that extra voltage so that if it does suddenly pull 300, you still have enough voltage to maintain stability. But the really big problem that you run into is that you can get all of the cores active without there being much current draw, right? If you watch the videos where I actually catch like the really big voltage spikes with the 125 microcode, those voltage spikes happen at the start of Cinebench 15 and at the end of Cinebench 15. At least that's the most common place that you see them. You also sometimes see them during Windows startup. Other Cinebench versions also do it sometimes. So yeah, like various all-core workloads can basically randomly unload while keeping all of the cores still awake. And when that happens, the CPU is sitting there like, well, the cores are active, so theoretically, any microsecond, I could start running Prime 95 small FFTs, right? And if I start running Prime 95 small FFTs, I will pull 300 amps. And if I pull 300 amps and the voltage regulator is set to 1.1 milliohms of load line slope, then the voltage is going to droop by 330 millivolts. So I need to send a VID request high enough that even if the voltage does droop by 330 millivolts, I don't crash. And so, like any all-core workload, because of this, ends up sending the same VID request as Prime 95. Actually, Prime 95 eventually ends up with a higher VID request because of the higher operating temperatures. But basically, literally any all-core workload has like the same VID request as Prime 95. If they were also at the same temperature, which they aren't, but yeah. And the most extreme examples of that, like 24 cores active but not actually doing anything, is, funnily enough, the Asus BIOS. Yeah. The Asus BIOS, for some reason, in certain, like with certain settings in the BIOS, actually, when it starts up, it very consistently does this. Like booting an Asus motherboard very consistently, like if you're on a microcode older than 129, will just smash 1.6 volts into the CPU. Assuming that, like, that is assuming that you set the load line to 1.1 milliohms, because if you're, like, well, we'll get to that. But if you have a 1.1 milliohm load line on an Asus motherboard on a microcode older than 129, it will just smash 1.6 volts into the CPU right as the board starts. And then sitting in the BIOS, it's actually not that bad. But if you, I think, turn off C states in the BIOS or something, then you'll actually sit in the BIOS at 1.6 volts. Because all of the cores are active, and the 14900K's power management is going like, man, any minute now I could start running Prime 95, gotta have that voltage. But you're sitting in the Asus BIOS, and so you're not actually pulling any current, and so you get massive voltage. Because there's no, you know, like if the CPU is pulling 10 amps, there's not going to be any V droop to pull that like VID request down. And so the CPU gets 1.6 volts, and the CPU very rapidly degrades because of that. But the other thing is, like, yeah, if you're running all-core workloads in Windows that don't actually hammer, like, don't peak very high current draw, you get very high voltages. Because this load line system is not fit for purpose with 300 amp CPUs. Like, this is just not viable. You can't do this. So, yeah, like, and the thing is, like, I understand how Intel ended up with, like, this setup of, like, hey, we're only gonna, you know, we're gonna scale the VID request based on how many cores are active, so that if you're, like, single core boosting, it's not actually, like, it's not gonna request insanity most of the time. But the problem is, like, yeah, but what if you get the prediction wrong? Because you can't see into the future. Just because all of the cores are active doesn't mean you're actually going to run Prime 95 small FFTs next, right? You might just run Cinebench. You might run something that's less heavy than Cinebench, right? Cinebench still pulls, like, 80% of the power that Prime 95 does. So you're going to get, like, 80% of the V-droop that Prime 95 does. But if you're running something that's like 50% the load of Cinebench, or God forbid the Asus BIOS, which doesn't pull any current, and the cores are all active, you just get massive voltages. And so this is just a really, like, clunky way of dealing with this, right? And the thing is, if you have a garbage tier motherboard, like, you still have this problem. Like, this isn't a problem of, like, if you put 1.1 milliohms of load line slope on a high-end board, the board just has more V-droop than it needs, right? It's not like if you put 1.1 milliohms of load line slope on a garbage motherboard that actually has 1.1 milliohms of like board impedance. If you're pushing, 10 amps into the CPU and the CPU sends a 1.6 volt VID request, well, it's going to get 1.58 something volts. Right? Because it does, like, this doesn't matter. So this is the thing. Is just like, yeah, this load line system is like, I am surprised that Intel took so long to add a VID limiter to the microcode, because the massive like 1.6 volts and higher voltage spikes that, I measured with the oscilloscope on the 125 microcode, they're just inherent to this power delivery system. Like, you're just going to run into situations where all of the cores are active, but nothing is actually running. And when that happens, you get 1.6 volts. I don't know how they thought this was not going to happen. Right? This is also why they're like, oh, you mustn't use high performance mode, because high performance mode might keep the cores active even if they're not doing anything. And then you get 1.6 volts and it degrades your CPU. It's like, hey, Intel, have you considered maybe designing a power delivery system that doesn't have the potential to wreck the CPU if it just happens to be running in a slightly weird situation? Which apparently they are capable of doing that, as demonstrated with the 129 microcode, but it's just like, how did they come up with this? And the thing I really, really don't understand is that in all of my testing, even if you set the boards to 0 milliohm load line slope, so massive undershoot, right? And then you set your AC load line to 0 milliohms, I've never seen this actually negatively affect its stability. Now, I wouldn't recommend that you actually do this on most motherboards, because your voltage regulation ends up looking like this. I'm too far down the page, but yeah, like you end up with massive overshoot. Like you end up with like even on an Apex at level 7 LLC, which level 7 isn't 0, it's like 0.2 something. At level 7, there's like 100 millivolts of overshoot, there's 100 millivolts of undershoot. The CPU is still stable because Intel does have some clock stretching capability, not to the degree that NVIDIA does. NVIDIA's clock stretching capabilities are wild. Like if you can get NVIDIA GPUs to like run at like 0.7 volts while reporting an operating frequency of 2 gigahertz because of how much they can clock stretch. You can't do that with Intel CPUs. If the average voltage gets too low, Intel CPUs will still crash. But like short spikes of undershoot, the Intel CPUs seem to actually handle those just fine. But yeah, even on high-end boards, if you set your load lines to 0, the voltage regulation gets pretty bad. And if you had like a crappy motherboard where, say, the control loop of the voltage regulator isn't super stable, you could end up in a scenario where like rapid transients cause the voltage regulator just to go completely out of whack. And so, yeah, like I wouldn't recommend that you actually like set super low load lines everywhere, because while it doesn't destabilize the CPU, it could actually destabilize the voltage controller, which would be worse. Because, yeah, you'd be back to basically degrading the CPU very rapidly if that happened. So, yeah, so this is like, and this is probably like, you might remember I made a video about how like Minecraft servers are burning through i9 14900Ks like super fast, right? And in that video, we actually looked at like the hardware info report from those super micro boards. Well, those super micro boards use a 1.1 milliohm load line slope, and they're on really old microcodes. So yeah, those boards, like, I don't like that. If that Minecraft server software keeps the cores awake, hello, 1.6 volts. Like, and the fact that so yeah, this is just, as far as I'm concerned, this is just an inherently unsafe power delivery system. And Intel with the 129 microcode like finally decided to rein it in. Right? It's like, you know what? Maybe we shouldn't give the CPU the ability to kill itself. Just an idea. Now, the other thing that was going on with LGA1700, which is like possibly why it took so long for like people to notice this, is the AC load line undervolting. So this is a separate issue. This is why, like, you may remember there was like articles about like people mass returning i9s in Korea when Tekken launched, because yeah, i9s, like, you couldn't get through the shader compilation for that game with an i9, and the reason why that happened is so let's say Asus, so Asus, for example, had the following VRM settings: VRM LL equals 0. No, actually equals 1.1 milliohms. AC LL equals 0.55, and then DCLL equals 1.1. Now, DCLL is literally just used for calibrating power measurements, so it doesn't affect the VID requests at all. So that's why DCLL, like in the Asus configuration, it's 1.1 to match the VRM, because if DCLL, like if we set this to 4, this will make the CPU think that it's pulling way less power, and if we set this to 0, it'll make the CPU think that it's pulling more power. So if this isn't properly matched to the VRM, you basically, it's like it's basically like changing the power limit is what the DC load line does. If it's not properly matched to the load line of the VRM. So that's like, so basically the DCLL is generally well matched. Now, Gigabyte, which I'm just going to go for GB, would have a VRM LL of 1.1. At least on the boards that I've tested, it might be different on the semiconductor boards. An ACLL of 0.4 milliohms, and a DCLL of I think 0.9 milliohms. So for some reason, Gigabyte is actually over-reporting the power consumption to the CPU a little bit. I kind of suspect that Gigabyte just doesn't know what these two do, so that's how they ended up with that. And then MSI. Now, MSI, unfortunately, I have no idea what their VRM LL is. So VRM LL equals no idea. I haven't looked into figuring out what it is yet. ACLL equals 0.5, and DCLL equals 0.8. So I'm guessing the VRM is probably somewhere close to 0.8, because I suspect MSI is a bit better informed about what DCLL does than Gigabyte is. But yeah, so this is probably like 0.9 or 0.8. Or yeah, like it might be something like that. But anyway, so the result of doing things like this with your load line settings, I'm going to run out of space. So we're just going to scrap MSI because it doesn't matter. We're just going to go with like Asus for the calculations. So the reason that even a brand spanking new i9, factory sealed, you know, you have like the little sticker factory seal still there, brand new i9 CPU, you stick it into your high-end Asus motherboard, and then you try to run Tekken and it can't compile shaders. Well, the reason that happens is because the CPU would make VID requests with the assumption that there's 0.55 milliohms of V droop, but actually there is 1.1 milliohms of V droop. So what would happen is, let's say the VRM, or let's say the CPU is pulling, so let's say we're trying to run 5.6 all core again, right? So 5.6, just for consistency, and we're going to do it at 1.3 volts, right? So at 0 amps, right, we just request 1.3 volts because there's no V droop. But at 100 amps, right, to get 1.3 volts, we do, okay, 100 amps times 0. Why did I go with ASUS? Let's just take that off. 0.5. So we need plus 50 millivolts. Now, obviously, I'm leaving out the part where the actual current that is used for the AC load line isn't the current that the CPU is currently pulling, but the current that the CPU thinks that it could be pulling. But for simplicity's sake, we're just not gonna worry about that right now, right? So the CPU is like, okay, I'm pulling 100 amps, so I need to, there's 1.5 milliohms of load line slope. I'm going to need plus 50 millivolts, so it sends a VID request for 1.35 volts. The VRM gets that request, right? VRM gets this 1.35 volt, so this is the SVID. So it sends 1.35 volts over SVID. The VRM gets that, goes minus 1.1 milliohms times 100 amps. And you end up with 1.24. Yeah, you end up with 1.24 volts. So, CPU needs 1.3 volts to function, actually gets 1.24. But this is not a big deal. A 60 millivolt undervolt is probably not going to crash your i9. But let's say the CPU is pulling 200 amps. So that's going to be, plus 100 millivolts. So we send a 1.4 volt SVID request, right? And I've really botched this. So we send 1.4 volts over SVID. And then we do minus 1.1 milliohms times 200 amps. And, well, that's 220 millivolts, so we end up with 1.4 minus 200 is 1.2 minus 20. We end up with 1.18 volts. Ah. Well, this is like 120 millivolts worth of undervolting. The CPU might actually crash at this point. And obviously, as the current draw increases, right, this trend continues of basically what this does is your CPU gets more and more undervolted the more power the CPU is pulling. So if you're just doing stuff on the desktop, you don't really have an undervolt. If you're running mild workloads, you don't really have an undervolt. And then when you hit something really, really heavy, suddenly the CPU is getting 120 millivolts less than it should be, or maybe even 200 millivolts less than it should be. Because yeah, let's do the math for 300 amps. Right, so this is going to be plus 150. So our request is going to be 1.45. And then it's going to be negatively offset by 330 millivolts, which is going to be 1.0, because minus, it's going to be minus 1.1. I'm just going to write it out. This doesn't actually help me do it in my head, does it? But whatever. So that's going to be 1.1, 1.15. So we're going to end up at 1.12 volts. Right? So you get this progressively increasing undervolt the more power the CPU pulls. And so if, there's a big current spike for a fraction of a second while running some workload, which, when the CPU, this is a funny thing, is you're going to, that 5 point, Intel's power management is really fast. So for comparison, the shortest power state transition I've seen on AMD CPUs is a millisecond. So the voltage level will change every millisecond based on temperatures, power consumption, that kind of thing. Intel, as far as I can tell, can do it every 0.1 milliseconds. So you could actually end up in a situation where the CPU boosts to 5.6 gigahertz for like 0.1 milliseconds, blips 300 amps, gets a big fat undervolt, and crashes. Lovely. Right? So that's kind of the, and so like when you're running other workloads, like say Cinebench 23, which runs at like 5.2 gigahertz, it doesn't look like there's anything wrong with the CPU. But if you run something where, you know, the workload is very spiky, it's suddenly really unstable because for brief moments of time, the CPU is getting, like, depending on how much peak current there is, you get different undervolts. So yeah, not great. So this is like the AC load line undervolting that was happening. Now, the funny thing about these AC load line undervolts is that they do kind of prevent the problems that Intel's load line slope system has, right? So the gaming motherboards are actually less susceptible to the, or at least used to be less susceptible to the really high voltage spikes until the 125 microcode came out, because they were undervolting the AC load line, right? Like this whole issue of like, oh, if 24 cores are active, 307 amps times 1.1 milliohms, well, it's a lot less of a problem if you just 0.55, right? And so this is now like plus 150 millivolts instead of plus 300. So now you're like 1.3 volts plus 150 is like, not, you know, you don't get the massive, like the voltage spikes are somewhat reduced. They are still there. Like some of the, like, well, I mean, the 125 microcode is like especially bad. That one, as far as I can tell, is probably actually the least safe, because Intel basically went and like they blocked the AC load line undervolts, but they didn't, like, you don't have the VID limiting yet. So you're just left at the mercy of Intel's just ridiculous load line slope system. But but even on the earlier microcodes, you do still get some pretty nasty voltage spikes. They're just not quite as bad as they are on the 125. But then you have like OEM motherboards, right? Like the Supermicro servers, those don't do any AC load line undervolting, right? They run a 1.1 milliohm AC load line. I'm sure if you hooked up the oscilloscope to one of those Supermicro boards, it would be hitting 1.6 volts all over the place. So, and this does kind of make me wonder how bad this is for like system integrators like HP, Dell, Lenovo, because the motherboards they build are trash. And I would not be surprised if every single one of those boards had a 1.1 milliohm load line slope so that they can shave off as many capacitors as physically possible. But if those boards have a 1.1 milliohm load line slope, that means anytime the CPU has 24 cores active, it's liable to request like 1.6 volts unless they're manually lowering the ICC max in the BIOS. So yeah, like Intel's, and also what's crazy is because the AC load line, like, so as with the AC load line undervolting, right? Like Asus, Gigabyte, MSI, they were all getting away with like 100 millivolts plus undervolts right out of the box, right? So Intel is shipping these CPUs with a big fat safety margin from the factory, right? Like your i9 can probably undervolt by 100 millivolts if it's using the like Intel AC load line, right? Like AC load line recommendations. So if you have a like crappy OEM motherboard with 1.1 milliohms of load line slope, that CPU actually is running a bunch of extra voltage most of the time, right? Because anytime the CPU isn't pulling the expected peak current, it actually has a bunch of more safety margin than it normally does. So if the CPU is like the point at which you notice that the CPU has degraded is when all of the safety margin is gone, right? So if the CPU comes from the factory with 100 millivolts of safety margin and it loses 5 millivolts of safety margin every 2 months, it'll take like 50 months before you notice that the chip is dead. And that's assuming that it doesn't have a bunch of extra voltage due to the AC load line, right? Because like basically your safety margin is gonna like wear away slower for something like Cinebench than it is gonna wear away for something like Prime 95. Because when you hit Prime 95, you end up in that. I'm gonna bring back the peak current thing. Hopefully, I grabbed the right one. Okay, I did. Because I have 2 instances of this open for some reason. So like here, right? Like this is the same load line slope. If you always just stress tested the CPU with Cinebench, Cinebench would actually tolerate 30 millivolts more degradation than Prime 95 does. Right? So if you never load the CPU to 100%, it's going to take significantly longer to notice that it degraded. And so, yeah, like this is like this situation is just kind of wild because you have so many different problems at the same time. Like for one thing, you have the AC load line undervolts from the motherboard manufacturers, which destabilize even brand new CPUs with no degradation. Then you have the fact that Intel's load line like implementation for LGA1700 is actually insane and inherently unsafe. So if you put it under the wrong kind of workload, it'll just try to kill the CPU. And then because this like load line system also just like overvolts the CPU, which is like, yeah, that's just what it does. If you have it actually the more load line you run, the longer it'll take for you to notice the degradation caused by the excessive voltages. And it took them 2 years to realize that maybe, just maybe, it would be a good idea to prevent the CPU from sending VID requests greater than 1.55 volts. Like, I actually just cannot. So, the main thing I want to make clear is that the degradation of these CPUs is, well, okay, I don't know, I don't know for sure that, because other things the motherboard vendors were doing was disabling things like CEP, which limits the peak current that the CPU can pull. They were disabling ICC max. They were disabling the power limits, though I really think the current limits are more important than the power limits, but whatever. So they were disabling the power limit. So, and the thing is, there's multiple types of degradation that you can suffer in a chip. If you just heat a chip to a high enough temperature, at some point you'll kill it with temperature alone. But you can also destroy a chip with just high voltage, right? Which is what Intel's load line implementation will do. If the thing is, that 1.1 milliohm number is literally in Intel's own documentation as the maximum load line that you can use. And it's just but if you use that number, you get 1.6 volts. What are they doing? How did that number make it into the documentation? And what's more crazy is that for laptop CPUs, that max load line slope is 1.7 or higher even. So and then they have this predictive VDROOP compensation where it's yeah, and if the prediction is wrong, then the CPU dies. Amazing. Wonderful. Just truly, I don't know what they're doing. I mean, I understand why it works the way it does, because yeah, it's kind of awkward if your CPU has, if the motherboard has a 2 milliohm load line slope or a 1 milliohm load line slope, and then it VDROOPs to the point that the CPU crashes. Yeah, that's probably not ideal. So yeah, you do kind of need to make sure that the CPU has enough voltage. but maybe don't send VID requests that will kill the CPU if the VDROOP doesn't happen. Just saying. That might be a good idea. Anyway, where was I going with this? Right. That was a reflexive write. Yeah, so you can have like multiple different forms of degradation, right? You have degradation due to excessive current, degradation due to excessive voltage, degradation due to excessive temperatures, and the motherboard vendors were disabling current limits and power limits. So that would, like, if these CPUs were also susceptible to excessive current, then yeah, disabling things like ICC Max would cause the CPUs to degrade when running all core workloads at even very low voltages, right? Because a 14900K, you can pull that 307 amps at like 1 volt. Or, okay, not 1 volt, but like 1.1 volts if you run something like Prime 95 small FFTs. Like, yeah, you can pull 300 amps. So you don't need a crazy high voltage to pull insane amounts of current on a 14900K. So if the 14900K is susceptible to electromigration degradation at like 400 amps or something, then yeah, turning off the current limit is probably not good for the longevity of the CPU. But at the same time, the CPU is definitely susceptible to degradation due to excessive voltages, and that is entirely Intel's fault. Because this VDROOP compensation system is like, why would you bolt this on top of, this is why NVIDIA doesn't do this, right? Like, NVIDIA, like, if you think about a 4090, right? A 4090 probably has a peak current somewhere in like the 500, 600 amp range. NVIDIA completely gave up on this style of load line system with the GTX 900 series. The 980 Ti has a like better power delivery system than a 14900K. Because GPUs are inherently just extremely noisy in terms of like transient loading. So yeah, if you used an Intel style freaking load line system on a GPU, like you would never be able to make a functional GPU. Or at least not a fast functional GPU. You could always clock it so low that, it wouldn't need very high currents or something, but yeah, like if you applied this style of power delivery to a 4090, like it would just not work at all. So, and on that note, AMD also uses a more NVIDIA style power delivery system these days, where the motherboards come with extremely shallow load line slopes, and then the CPU just clock stretches whenever there's undershoot. But Intel has this like Sandy Bridge era load line slope system, and then they're like, well, now we have 300 amp CPUs, so I guess we just compensate for 300 amps worth of VDROOP at 1.1 milliohms. That seems totally sensible. And if the VDROOP doesn't happen, then I guess the CPU just dies. So yeah, like so like this, like the voltages, the insane voltages, Intel's fault. The no power limits, maybe the motherboard vendor's fault. Personally, I don't think that the current limits and the power limits have anything to do with most of the degradation that people are seeing, because again, those super micro servers had all of the power limits, all of the current limits. The only thing they did wrong was they followed Intel's load line specs. That was the only thing that you could fault those super micro boards for, is like, yeah, they like followed the specifications that Intel put into their documentation. Is like, so that's Intel's fault. And is there anything else? So yeah, but then the other point is that a lot of the like out-of-box instability on brand new CPUs is actually just the motherboard vendors undervolting the CPUs. So that's like a separate issue. That's not actually degradation. If anything, the fact that like Asus, Gigabyte, and MSI, and they were all undervolting the CPUs probably slowed down the degradation. significantly on the gaming motherboards. So, admittedly, they turned off all the power limits and stuff, but at least your CPU was getting undervolted a bit. They also removed things like TVB TVB is supposed to prevent your CPU from boosting to 6 gigahertz if it's above 70 degrees Celsius. Yeah, that didn't work on like some past microcode versions, so the CPU would still go to 6 gigahertz even at like 100 degrees. Um, so, you know, but like the high voltage spikes, that's Intel. That's entirely Intel because no motherboard that I've tested is like adding extra voltage to the output. That's not a thing. So, yeah. And I really don't get why Intel didn't just, like, they have clock stretching in these CPUs as far as I can tell. Why didn't they just recommend, like, why didn't the spec just say that you're supposed to use like a 0.3 load line slope for everything? Because, like, they have to, like, the thing is, I don't even know for sure what the, like, expected peak current that is used for the V-droop compensation is. Like, again, with the i5 data that I have, it seems to be more than the ICC max, which would make sense. Right? Like, the ICC max for an i5 at, like, stock is supposed to be 200 amps as far as I know, but you can see that the peak voltage actually goes up all the way to 250. It doesn't go up at 500 amps because evidently that's not, there's no way an i5 is ever going to pull that much current. So it doesn't need to compensate for that. But I guess it like could pull 250 or 225, and so it does compensate for that much. Right, and you can see how like as the ICC max get slower, the VID requests get lower. Though some of that is also just going to be like power limiting, like the CPU getting power limited, so like not reaching the higher boost states for some of this. Yeah, so like my point is like I don't even know what the peak current that Intel is doing the compensation with is. Intel knows what that is. Like they designed this. And if you do the math on it and go like, hey, but what if just freak scenario, right? For some reason, some software lights up all of the cores, but doesn't do anything with them. What happens to the CPU in that scenario is apparently a question Intel never asked. And also that scenario happens like anytime you start or stop an all-core workload, which is just kind of funny. Like, so it's actually kind of common. And it's just like, yeah, it'll be fine. We just, so anyway, that's there. Like, now I've gone through everything, I think. And, yeah, like, key takeaways is like, the voltage regulator measures the voltage at the CPU. Okay? Like, that's one of the other like big frustrations I've had with seeing a lot of the discussion is like the load line is like the impedance of the board in steady state is irrelevant. The voltage regulator will compensate for that on its own, but it can't compensate for it during fast load transitions. And that's why we have load line slopes. And then because Intel, for some reason, went with really deep load lines, probably because here's the thing, the socket itself probably has like 0.2 milliohms of resistance, right? So if you set like 0.2 milliohms as your load line slope, like your voltage regulator would basically have to live on the other side of the CPU socket, right? Like where the backplate is, that's where the voltage regulator would have to be. And even that probably wouldn't be enough because, again, the voltage regulator itself has lag, which basically translates into more impedance. So, yeah, so this is just like there. Anyway, but yeah, like my main frustration is I've seen people saying like, oh, the load line slope is for compensating for like that's not what it's for. It's for load transitions. if your CPU pulled 300 amps all day every day, we wouldn't need load line. Like, we literally wouldn't need load lines. But because your CPU doesn't pull 300 amps all day every day, we do need load lines. Because when it goes from pulling very little current to pulling a lot of current, you need to, like, deal with that. And load lines is how, well, we've been dealing with that for several years. Unless you do what NVIDIA and AMD did, where you just let the chip deal with the fact that the voltage is really low for a bit. Anyway, there. Okay, now I think I've actually said everything I wanted to say. So that's it, I guess. So thank you for watching. Hopefully at this point it makes sense. Like what is going on with load lines on LGA1700. Yeah, man, I don't know why I'm struggling so hard with the outro here. I'm just worried that there's like some little thing that I might have missed and I'm gonna get to read some incredibly stupid comment after recording an hour 40-minute video. And somebody still isn't gonna get it. Anyway, thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. And if you'd like to support what I do here with the channel, I have a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store. There's a link to that in the description below. And I've also got a Bandcamp. And I'm also working on a game. There's links to all of that in the description. I'd appreciate it if you check them out. And that's it. So thanks for watching, and goodbye.